In this video, we're going to introduce probability. So we'll talk about different approaches to finding the probability of an event. And in general, when we say what's the probability of an event, what we're asking is how likely it is to occur. So here are a few definitions that will help us with our discussion. An event is a collection of results or outcomes from a procedure or an experiment. A simple event is an event that cannot be broken down any further. And the sample space for a procedure consists of all possible simple events for that procedure. So let's look at a basic example. Suppose we toss a coin 3 times, and each time that we toss that coin, it can be either a head or a tail. Let's figure out what the sample space for this procedure is. So one way we can visualize that is by thinking about a tree diagram. So we can have our first toss can either be a head or a tail. Our second toss, well, after it was a head, it could be a head or a tail. And after it was a tail, it could be a head or a tail. And finally, our third toss, after it was a head, it could be a head or a tail. After it was a tail, it could be a head or a tail, and so on. And so this is a tree diagram diagramming each of the possible events or each of the possible simple events. So each of the individual branches, so if we think about following a branch all the way through, that corresponds to one simple event. This first one would be that the first toss was a heads, the second toss was a tail, and the third toss was a head. Whereas a different branch, like say this one, corresponds to the simple event that we had a tail and then a head and then another head. So the sample space for this procedure, the sample space is our set of all simple events, and in this case that's HHH, 3 heads in a row, or HHT, 2 heads and a tail, or head, tail, head, or head, tail, tail, or tail, head, head, or tail, head, tail, or tail, tail, head, or tail, tail, tail. So there are 8 simple events in the sample space for this experiment. And do note that, for example, the simple event head, head, tail is not the same as the simple event head, tail, head. And we'll see why that's important later on in the video. Counting those as 2 simple events is really important for finding accurate probabilities. One other important thing to note here is that an event like 2 tails in 3 coin tosses is an event, but it is not a simple event. And it is not a simple event because it can be further broken down into 3 separate simple events. So 2 tails in 3 coin tosses could be tail, tail, head, or tail, head, tail, or head, tail, tail. So those are 3 different simple events that the event 2 tails in 3 coin tosses breaks down into. So in general, we use capital letters like A and B to denote events. And if A is an event, we use P of A to denote the probability that A will occur. So the main approach to probability that we will use is called the classical approach to probability, and it requires equally likely outcomes. So the classical approach to probability says that the probability of A is equal to the number of simple events in which A occurs divided by the total number of simple events. So as an example with our coin toss above, if 3 coins are tossed, what is the probability of exactly 2 heads in the 3 tosses? So we saw above that we found our sample space. And so when we think about the probability of our event A, A in this case is exactly 2 heads in 3 tosses, so this is our event A. What is the probability of that occurring? It's going to be the number of events where A occurs the number of simple events where A occurs divided by the total number of simple events for the whole experiment. So for us, we saw that there were 8 simple events in the sample space as above, and now which simple events are have A occurring? The ones with exactly 2 heads in 3 coin tosses. So let's see, this has exactly 2 heads, this has exactly 2 heads, and this has exactly 2 heads. Everything else has 1, 0, or 3 heads. So 3 of the simple events have exactly 2 heads in 3 tosses, and so the probability of our event A is 3 out of 8. So let's think about another example. Suppose there are 3 people running in a mayoral race. Then is the probability that each one of them will win equal to 1/3? If these were equally likely events, the answer would be yes, but generally the answer here is no. Generally, there's a whole lot of other information. One mayoral candidate will be more likely to win than another, and you can find that out based on polling or various other data. But in general, if you have a presidential election or a mayoral race, or is it going to rain tomorrow? Even though it could rain tomorrow or not, that doesn't mean that the probability is 50-50 every time. But you can get a better idea of the probability, by checking out the weather or something. So no, and the reason is that these are not necessarily equally likely events. And that's in comparison to things like, tossing a coin or picking a card out of a deck, or, if you've got a probability distribution for whether a product will be defective or not, and you're randomly selecting a product, or like lots of other things that we can think of as equally likely events. So we can only use the classical approach to probability when simple events are truly equally likely, but there might be situations where we don't necessarily know that those simple events are equally likely, and we can still use the classical approach as a baseline to help us begin to think about some probability. Probabilities are usually expressed as decimals or fractions, not as percents. So I'd like you to think for a moment, what is the probability of an event that is impossible, and what is the probability of an event that is certain to occur? And based on that, for any event A, that means the probability of A must be less than or equal to something and greater than or equal to something else. So I would like you to come up with values for each of those blanks, and we'll talk about it in just a second. So the probability of an event that is impossible is 0, and the probability of an event that is certain to occur is 1. So this is 100% if you convert that to a percent, and this is 0%. But as I said, we mostly use fractions and decimals to talk about probabilities. So that means that for any event A, the probability that A occurs must be less than or equal to 1 and must be greater than or equal to 0. So this is a good place to check when you're doing your work. If you ever have a probability that is larger than 1, something went wrong. If you ever have a probability that is less than 0, something went wrong. So this is just something to keep in mind as you're doing probability problems. So we'll primarily use the classical approach to probability in this course, but I wanted to talk briefly about 2 other approaches, the subjective approach to probability and the relative frequency approach to probability. So the subjective approach to probability is using knowledge of relevant circumstances to estimate the probability of A. So for example, you could say, what's the probability that I'll pass this course? And relevant knowledge you might use Could be, your past performance in other courses, how well you're digesting the material so far, and so on. So let's just look at two together. What's the probability that a meteor will hit my car next week? And what's the probability that somebody in this online course is from Boston? So estimating those probabilities, the probability that a meteor is going to hit my car next week, it's not exactly zero because it technically could happen, but I could write 1 over, a very, 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 very large number, and 1 over a billion, for example, and maybe that is an estimated probability. It's not necessarily the exact probability, but it's just signifying that based on my knowledge of relevant circumstances, the probability that a meteor will hit my car next week is very, very, very small. When we say, what's the probability that someone in this course is from Boston? Well, it's very likely. If you yourself happen to be from Boston, then you know that the probability that someone in this class is from Boston is 1 or 100%. But if you're not from Boston and you're not certain that anyone else is, but you think it's pretty likely, you could say, 0.85 or something like that, that there's an 85% chance that someone in this course is from Boston. You might have said 95% or 0.95 or whatever, but unless you know for certain that someone is, 1 isn't quite correct, but it's more likely than not that someone is from Boston. Another approach to probability is the relative frequency approach. So with the relative frequency approach, we conduct or observe a procedure or an experiment and count the number of times that event A occurs. And then the probability of A is approximated by the number of times that A occurred divided by the number of times that the procedure was conducted. Notice I used a squiggly equal sign there to say that this was an approximation, whereas in the classical approach to probability, I could actually use an equal sign because I'm making the assumption above in the classical approach to probability that all events are equally likely. So in the relative frequency approach, we're getting an approximation, and the law of large numbers says that as the experiment is repeated, the relative frequency of the event approaches the true probability of the event. So we are, the more an experiment is conducted, the closer we are to the real true probability of that event. Some examples would be a batting average in baseball. So a batting average is the number of times that the player makes it to first base, divided by the number of times that they've been at bat. That's the batting average. And another example would be, say, like most polls, like say a political poll or, just a poll about public opinion. The more people that you ask, as long as you got a good random sample, the closer you will get to the true proportion of people who will vote for that candidate or have that opinion or whatever. And so anytime that a sample is used instead of the entire population, we'd be talking about the relative frequency approach to probability. And this first section on probability will generally be used in the classical approach, but later on when we talk about hypothesis testing and confidence intervals and that kind of thing, we'll be coming back to the relative frequency approach to probability. One more example is, say, weather prediction. This is really a mix of the relative frequency approach and the subjective approach. So with weather, a meteorologist would both be using previous data, like, out of all times that these clouds were observed at 9 p.m. on a Wednesday, this proportion of the time it rained by 2 a.m. on a Thursday or whatever. But they're also using some subjectivity to make determinations in predicting weather. The last topic I want to briefly touch upon is the complement of an event. So the complement of an event A is the set of all outcomes in which A does not occur. and it's typically denoted by A with a C in the superscript or A with a overline. So either of those can denote a complement. So for example, if a coin is tossed 3 times and A is the event of at least one tail, what is a complement? So here we're not asking for the probability of anything, we're just asking what is the event A complement. So if A is the event of at least one tail, then A complement is the set of all events in which there is not at least one tail. So the event A complement is, well, if there isn't at least one tail, then there are no tails. Or it could also be expressed as all heads. And let's also think about the probabilities of each of those events as well. So let's think about the probability of A complement, and let's think about the probability of A. And actually, I'm going to pause the video again for you to find the probability of A complement in this case and the probability of A in this case, and also to think about the relationship between the probability of A and the probability of A complement. So do you know how you could describe the probability of A complement in terms of the probability of A? So pause and think about those 3 questions just for a moment. We'll talk about them in a minute. Okay, so what is the probability of A complement? The probability of no tails, or that could also be expressed as all heads. Well, based on the sample space that we came up with before, there's only one simple event in which all of the tosses are heads, and so that's 1 out of the 8 simple events. What's the probability of A? A was the event of at least one tail, and we can see that in all the remaining events, at least one of the tosses are tails. So 7 out of the 8 simple events have at least one tail. So we were also asked to figure out if there was some relationship in general between the probability of A complement and the probability of A. So note that if we have an experiment, then either A or A complement will occur. So that means that the probability of A plus the probability of A complement is certain to occur. And because it's certain to occur, that means that its probability is 1. So we could then subtract off from both sides probability of A, and that means that probability of A complement is equal to 1 minus the probability of A. That is a really useful thing to know. We could, of course, also write that as probability of A equals 1 minus probability of A complement if we instead chose to subtract probability of A complement from each side. So both of those things are true statements. But there will be situations where it's much easier to calculate the probability of A complement than it is to calculate the probability of A. And so this could be really useful in calculating one or other of those probabilities. Let's also just notice quickly that, yes, this statement works up here. 1/8 plus 7/8 equals 8/8, which is 1. Great. And as just one more quick basic application of complements, if there's a 38% chance of rain tomorrow, what's the probability that it won't rain tomorrow? We would want to convert that 38% to a decimal, 0.38, and the probability of no rain, we could say that our complement is 1 minus the probability of rain, so that's 1 minus 0.38, and we'd have 0.62 probability that it will not rain tomorrow.